Hi guys, I want to talk a little bit about a couple scientific laws that are really important to chemists. And the first is the law of conservation of mass. This is also called the law of conservation of matter. And we know that chemists as scientists are really interested in material things and in matter. And matter is anything that has some amount of stuff that makes it up, some amount of mass. That's how we would measure it in kilograms. And it takes up some amount of space. And some very intelligent chemists throughout history, including Antoine Lavoisier, who's really the one who's credited with the law of conservation of mass. He's a French chemist who was really important. He's kind of the father of modern chemistry. There were a number of father of modern chemistry, but Antoine Lavoisier did a lot to kind of bring chemistry into the modern era, and he did this through a lot of really precise measurements. He was also one of the ones who kind of standardized the way that we name chemicals, and he really did a lot of incredibly precise for the time with the instrumentation that they had measurements about mass and how it changes during a chemical process or a chemical reaction. So a chemical change is when some combination of elements reacts together, and then we end up with some other combination of those same elements. And during that process, what Lavoisier found is that total mass remains constant or stays the same, or it's conserved in that process. And so this plays out in a couple different ways. Let's look at the combustion of methane. Methane is a hydrocarbon. The chemical formula for that is CH4. Methane is one of the things that is obtained through the process of fracking, for example, and it's found in a lot of natural gas kind of sources. You might associate methane with cows. In fact, speaking of natural sources of that, when you react methane with oxygen, we say that it undergoes a combustion reaction. This is the same type of reaction that happens in a car engine, right? We react together some sort of hydrocarbons. Usually in car gasoline, we're talking about, octane and heptane and some combination of those with a few more carbons in them, reacts with oxygen, and then in your tailpipe it spits out carbon dioxide. It's kind of the carbon footprint that we worry about when we're thinking about climate change, and water, which is kind of the steam that you see coming out of that process as well. So methane does the same thing. When I react methane with oxygen, we end up with carbon dioxide and water. So we can solve problems then by understanding the law of conservation of mass that look like this. If I start with 15 kilograms of methane and I have 5 kilograms of oxygen, so these on this side of my reaction here are called my reactants. So total for my reactants, I have 15 plus my 5 kilograms, so I have 20 kilograms of my reactants. And again, we're measuring mass, or how much stuff something is made up of, and our SI unit for that is the kilogram. And then those things react together to form what are called products. They produce products. And it says that we produce 8 kilograms of carbon dioxide, and how much water is produced. So our products here, we have 8 kilograms plus kind of an unknown, right? Now the law of conservation of mass, or the law of conservation of matter, says that whatever it is that I start with, however much mass or matter that I start with, I have to end up with the same amount on the other side. So you can probably do the math in your head to figure out that your X here is going to be 12 kilograms. Right? Kind of intuitive. It feels intuitive at this point because it's a scientific law. It's been around for a long time. So this is the way that we understand the world. The amount of stuff that you start with has to be the amount of stuff that you end up with. And so, of course, what seems intuitive to us now, because this has been part of the way that we understand and interact with the world, seems a little bit silly to do math problems like this. But this concept is going to be really important when we're bringing in different ideas and we're ramping up the level of complexity of these types of problems. So this is just kind of an introduction. All right, so that's the law of conservation of mass. Now I want to transition into another important scientific law, which is the law of definite proportions. So the law of definite proportions is really important to chemists as well. It's also called the law of constant composition. Get my straighten that up a little. There we go. The law of definite proportions means that in a pure compound, there's Joseph Prost, that's our guy. In a pure compound, it always contains a definite ratio or proportion of elements by mass. Or we can kind of think about it as when we react things together, they're always going to form. They're going to react in such a way to where they combine together in a definite ratio or a constant composition for a particular compound by element mass. And this is going to be really important moving forward when we're thinking about the chemical formula of things, how many of each of these atoms react together to form specific compounds, etc. So Joseph Prost was around a little bit after Lavoisier. He was chemically combining things together. And so the way that this kind of plays out is it looks something like this. If I have 1 gram of sodium chloride, so that's table salt, right? Sodium is Na, Cl is chlorine. So sodium chloride here has 0.3934 grams of sodium in it. So in every 1 gram of sodium, there's 0.3934 grams of sodium. So then in the 1 gram of sodium chloride, the rest of it is chlorine, right? So I have 0.6066 grams of chlorine, and that's always going to be true. It's a definite proportion. This is always the ratio that we see, except when it isn't. But you know, for our purposes now, let's call it an always. It's rare that I write always, so I feel like I'm committing to things here. All right. So given this information, given this definite ratio or constant composition, then how many grams of sodium are there in a 2.5550 gram sample of sodium chloride? Okay, now because we have this ratio set up, we are looking for information about this particular number of grams of sodium chloride, and I'm asked the question about how many grams of sodium. So I want to end up with grams of sodium as my answer. And so if I'm kind of working backward, then I need to know how many grams of sodium are in a gram of sodium chloride. So when I'm thinking about setting this up with dimensional analysis, I always start with what I'm given, which is this many grams of sodium chloride. And then my next step, if we kind of think about the factor label method, or in our dimensional analysis here, we need to get rid of these grams of sodium chloride. So we need to divide out the grams of sodium chloride. So I need that on the bottom. I'm trying to get 2 grams of sodium on the top. And what relationship do I know between those? Well, I was given in the law of definite proportions that for every 1 gram of sodium chloride that I have 0.3934 grams of sodium. So I can use this then, this proportion, this ratio, this constant composition to figure out the number of grams of sodium. And when I run the numbers on that, I end up with 1.005 grams of sodium. And if we're checking our answer here to make sure that it makes sense, some sort of physical way, if we think about this as a percentage, because this is a whole, right? 1 out of 1, I have 39.34% of it, essentially by mass, is my sodium. So if I think about roughly 40% of this particular number, so that would be slightly less than 1/2. So that makes sense. So again, when we're looking at our answer, analyzing whether or not it makes sense, we're going to say, is it going to be bigger than the original number or smaller? Well, this is a percentage, so we're expecting it to be smaller. It's going to be positive or negative. It's going to be positive. How many sig figs is it going to have? Well, it looks like I'm going to be limited to 4 sig figs based on my number of grams of sodium there. So I end up with 4 sig figs in my answer. All right, so those are some important laws for chemists: the law of definite proportions and the law of conservation of mass. And as always, if you have questions, don't hesitate to reach out, and I will talk to you again soon.